areas that act as a priority scheme. Sorry again. Okay, so that acts as a priority scheme. DIFS and FISF, we'll see this later, okay? All right, so we've seen this the last time. So we go through this very quickly now. If a station has a way, a frame to transmit, it have to check if the medium is free first. If it's free, then it have to wait for IFS, okay? The reason it have to wait for IFS because there may be many stations waiting to transmit. So when we wait, some stations have to wait for SIFS and some have to wait for DIFS, all right? Now, and we said before SIFS is DIFS here. SIFS is shorter than DIFS, so whoever has to wait SIFS gets to go first, okay? And this person have to wait, okay? So that's why we have this priority scheme. So let's say a person have to wait only 1 millisecond. The other, sorry, let's say 10 milliseconds. The other person have to wait 20 milliseconds, then the person gets to go first. And this is where we sort out the priority. Now, whoever has the lower value to wait, check the medium. It's still free, then that station can transmit, right? Now, if at this point, if the station is not free, then the medium is not free, then the station have to wait. Same here, have to wait, right? So this is to avoid collision. That's the CA part. And then it waits until the current transmission ends. And when the current transmission ends, it have to wait IFS. All right, again, the reason here is so that people with higher priority, with SIFS, can transmit before people with lower priority, DIFS. And whoever gets higher priority will check the medium. If the medium is still free, then the person have to draw a value from a random interval, just like in Ethernet, and back off before sending, right? Back up before sending. So now assume 2 people, right? SIFS has higher priority than DIFS, yes. So let's assume SIFS is 10 milliseconds, it's 20 milliseconds, right? If you have to wait 10 milliseconds instead of 20, you have higher priority, right? All right, why we need exponential back off here? Now assume 2 people. I'm just using people, but they actually station, right? Assuming 2 people have the same FISF, so both of them wait for 10 seconds, right? Both of them wait 10 seconds. Now, and after 10 seconds, the medium is still free. Okay. Now, if both of them transmit, what do we have? What would we have if both of them transmit at the same time? You would have a collision, right? You could have a collision. So that's why, exactly, you have a collision. So that's why at this point, we need a mechanism to avoid collision. So both of them have to draw a random number, right? Actually, they would draw a random number while waiting here. While they're waiting here, they draw a random number, let's say N1 and N2, right? So let's say N1 and N2. Let's say N1, this person draw number 5, and N2, this person draw number 6, for example. Okay. Then at this point, they will count down, right? Person 1 will count down 5 time units. Person 2 count down 6 time units. All right. So this person count down 5 time units. When it reaches 0, this person can send, right? Now this person, it count down to 6 time units. But at this point, it cannot transmit immediately. right? Sorry, 1 second. Because at this point before transmit, it has to sense the medium. And when it senses the medium, remember P1 already sent, right? Because P1 sent after 5-time unit. When P6 at 6-time unit, it senses the medium. It knows that, oh, I cannot send because the medium is busy, all right? All right, so in that case, it has to repeat the cycle, all right? It has to repeat the cycle. Basically, is the medium still free? No, then it has to wait until the transmission end, okay? All right, so that's the main idea. So now we go into details, right? All right, so now the backoff interval we just said is binary exponential backoff. When the channel is busy, it chooses a backoff interval in the range of 0 to CW, okay? We've seen this before in binary exponential backoff in Ethernet medium access control, okay? So when the medium becomes idle, the countdown, it starts count down the backup interval. Okay, so that's what we have here. Okay, so when it's become idle, both of them count down. This one count down by 5, this one count down by 6. Maybe instead of 6, I put a bigger number, let's say 9. Okay, assume it's 9. All right. All right. If the medium becomes busy again, countdown is suspended. What it means is, after 5 units, P1 transmits, right? P2 still sensing the medium, and it see that the medium is busy. What it means is now it suspend the countdown. Now it has 4-time unit left, right? Because both of them count down at the same time. 5-time units, P1 sends. P2 detects the signal. So it knows, okay, now I have 4-time units left, okay? So it will suspend the timer. So now it knows that it has 4-time units left, okay? All right. And then when the medium becomes busy, free again, so when after P1 transmit, the medium becomes free, P2 has to wait 4-time units, okay, before it can transmit. It waits for 4-time unit, then it can transmit, okay? All right. So when the backup interval reaches 0, transmit the data, okay? So this is binary exponential backup for AO 2.11 medium access control DCF. When a node fails to receive acknowledgement, okay? So the assumption here is if a node sends and then waits for acknowledgement and never receive acknowledgement, what it means is the packet must have been lost, right? The packet must have been lost. So that's why CW is double, right? So that now you have to wait longer to avoid collision. Similar to in Ethernet, you double the interval so that you have to wait a bit longer in order before you can transmit, right? Up to an upper bound, okay? So we'll see the actual number later. But when the data transfer is completed successfully, CW is set back to minimum value. So the minimum value is 7. Okay, so that means the first time ever a station will draw a number from 0 to 7, right? And now if it sends data and then it does not receive acknowledgement, it will increase to 715. Remember, we double. And then it can send data. It draw a number from here. So let's say the first time it draw a number 4, right? Send data, did not receive acknowledgement. Double this interval, draw a number. So assume now it draw 10, sends data, does not receive acknowledgement, right? So it had to double to 31, sorry, to be 0, right? Draw another number. Now the number, assume I draw number 25, right? So that means I have to wait longer, okay? Now it may happen that I draw number 3, for example, right? Because this is an interval. But overall, if you have many people in the system, the larger the interval, the longer the waiting time, right? Because if I draw number 3, that means someone else could have drawn number 25 or 20, for example, okay? So this process going on until I can receive, I send data and then I receive acknowledgement, okay? If I receive acknowledgement, that means the transfer was successful. So now, if I start the sequence again and have the problem, I have to draw the first time. If I send data again, I have to draw a number from 0 to 7. Okay, this is reset to the minimum. All right. Okay, there's a question. So whenever a node is not received, backup interval is double. No, it's double, not plus 1. Double, not plus 1. So from 0 to 7, you have a value. From 0 to 16, you have 16 value. From 0 to 31, you have 32 value, right? The interval is double. There's no plus 1. Okay. When we say the interval, you mean the number of values within the interval. Okay. All right. Any question here? All right, so let's consider, so we're talking about SIFS and DIFS next, okay? All right, so this is one example. So this is the basic CSMA-CA operation, right? Okay, now first, the value of DIFS and SIFS. So DIFS is the longest, SIFS is the shortest here. And PIFS is in the middle, right? So if you rank them, this will be the ranking. So at the beginning, a station waiting to transmit, it has to sense the medium, right? It will senses the medium, and the medium is busy. All right. So when the medium is busy, it has to wait until. So when the medium is busy, first, it draw a random number, right? When it see that the medium is busy, it have to draw a random number. Why? Because when the medium becomes free, it have to wait for that amount of time. So in this case, it draw 1, 2, 3, 4, 5, 6, 7, 8, right? So the number it draw here is n equal to 8, all right? Exactly, DIFS and SIFS is a time interval that a station has to wait. Exactly, yeah, the time interval, okay? I know that the name is not really very intuitive, but that's what it means, yeah. Because the name means a short interframe space, right? You can see S here stands for space, but it's not really space, it's a time interval. All right, so it's draw 8, right? So when the medium becomes free, this station has to wait for the DIFS, all right? Now, if another station is waiting with SIFS, then this station can transmit before this station, right? So I call this station A, right? If another station is waiting for SIFS, it can transmit around this time, right? It can start sensing the medium around this time. So it can count down around this time, for example. But because A have to wait DIFS, so it wait DIFS, right? And then it will count down from 8, 1, 2, 3, 4, 5, 6, 7, 8. And it count down 8, then it sends the next frame, all right? And this is how collision is avoided, because assume you have another station B, which is also waiting, right? The medium is busy, so B has to draw a random number. So assume B draw number 12, okay? Then obviously you see that A transmit first, B transmit later. That's how you avoid collision. Because if you don't have, if they didn't draw these numbers, they transmit at the same time, that would be a collision, okay? So this is how collision is avoided, all right? So if B draw number 12, okay? Then at this point, when A transmit the frame, right? B knows that it has to suspend the countdown. What it means is now B has to value 4 in the countdown, right? N prime equal to 4 because it's already waited A time units. And then A sends. So now it had to wait for time units, for 4 time units, right? But it suspend the countdown to timer. Okay, so A would send this. All right, after A send this, what would happen next? Okay, so let me try to, Shadan has a question. Do you still have the question or is the hand from before? No, okay.
That's a hand from before.
Oh, right, that's fine. Yeah, okay, yeah. Okay, so now let's assume that we assume that we have another node, right? So assume at this point here, a node C, a station C want to send, right? Obviously, C can see that this is the medium is busy. So C will try a number, okay? Let's say NC, this NB, and this NA. So this NB prime. So C draw a number, let's say it draw number 10, okay? All right, draw number 10. Now both of them have two-way DIFS. Okay, so I'm going to the next cycle. Both of them have to wait for DIFS for sure, right? And when DIFS finishes, both of them have to count down. Okay, so it's the countdown. Now B has 4 time units. C had 10 time units. So you can see that B gets to transmit first, right? So it gets 1, 2, 3, 4, right? 4 time unit, right? So the same as this part here. And then B will send the frame. Okay, B send the frame. So this is the frame, okay? The frame from B. Now at this point here, C detects that the medium is busy, right? So at this point, remember C count down from 10. 4 time unit has passed. That means C still has 6 time units left, right? Agree? Any question there? It still has 6 time units left, right? Okay. So what it means is, sorry, Mary. When B finishes the transmission, okay, so I'll go down here. I'll go down here. So B transmitted. C have to wait for the DIFS. Okay, DIFS. All right. And then after this is countdown, right? And how many time unit does it have to count down? 6 of them. 1, 2, 3, 4, 5, 6 of them. Okay, 6 of them. And then after this, C can transmit. So this is the data from C. All right. Okay. So now anyone has any problem with this? Okay, Shadan, you have a question.
Yes, I had a question. So for the contention window, how do we determine like the number or like how many times the attempts have to be?
How many time units? What do you mean? Right. So so like I said, you draw a random number, right? Remember we have this. Remember I give this a sample.
Mm-hmm.
At the first ever you draw a random number between 0 and 7, right?
Yeah.
And if the medium and then the medium become free, you send data you did not receive acknowledgement, then you increase the interval up to from 0 to 15, right? And you draw a random number here.
And then just keep doubling until you receive an acknowledgement.
Exactly, right? So in this example, when I assume B draw number 8 and this one draw number 12, A draw number 8 and this draw number 12, that means they must have some collision before here, right? Because if there's no collision, you have to draw from between 0 and 7 first. Okay, yeah, and draw randomly between 0 and 7. Now, in this example, they draw randomly between 0 and 15. All right, 0 and 15. Okay, does that make sense?
Yeah, that makes sense. And one more question is, what is the NB prime? Like, what's the difference between that one and just NB?
It's after B true number 12, right? And it counted 8 time units. Agree?
Yeah.
You have to count out. You have a timer, right? Now it count out 8 time unit. It had 4 left, right?
Mm-hmm.
Right. So that's the number left, the timer left on your countdown. So basically, you have to wait 12 minutes to send, right? Or 12 minutes to talk, right?
Mm-hmm.
You already waited 8 minutes. You need to wait another 4 minutes before you can talk.
The 4, that's just what's left, right?
Exactly. Right.
All right, thank you.
You're welcome. All right. Any other question? Anyone has Aditya?
Hi, hello. I just had a question. You said that any station with the SIFS can still transmit during the BIFS time. Does that just have to do with priority of information, like that needs to be set?
Yeah, we will see SIFS later. Yes.
Okay.
Yeah, but for now, we assume that everyone has the same priority in this scheme. Yeah, right. We will talk about SIFS later. Yes. Shadan, you have a question again? Or was the hand from before?
It's the hand from before.
Okay, sure. All right. So, and it's easy to understand here, right? Okay. Now, a question for you. You see here, B suspend the timer, right? So it had 10 times, 12 time units. It waited 8 time units. Now it had to wait 4 more time units before it can transmit, right? Why at this point? Why didn't B draw a new number? You know why? Why does it have to suspend the timer? Why didn't make it simpler, draw a new number? You see what I mean? Instead of waiting for 4 time units, why didn't it draw a new number? Exactly. Yeah, Aditya, you're right. Because if B threw a new number, it may have to wait forever, right? Because let's say if it threw a new number, you can see, let's say now B threw a new number between 0 and 15, for example. It may draw number and B, this is B2, right? Draw second time, it may be 12, okay? If it draw 12 again, or let's say 13, right? 13 is a bad luck. 13, then you can see that C can transmit first because C threw number 10. B, if it threw number 13, it have to wait, right? And then who knows, maybe another station D joins. And then B have to draw a new number. And every time it draws a new number, it keep waiting forever, right? So that's why it doesn't draw a new number, but rather than keep the previous remaining timer and count down from the remaining timer. Okay, so that's the reason why. All right, so that's the basic CSMAC operation. Now we'll talk about why we need SIFS. Okay, all right, so same as before, we have the source, right? So assume the source is S, destination is D. The source waits for DIFS and then send data, all right? Now the destination have to send back an acknowledgement. This is when you can see SIFS is used. The destination have to wait only SIFS time units, all right? Why? Okay, so now the reason is assume there's another station waited to send. Okay, so assume there's a station B wait to send here. Now remember, B has to wait DIFS, right? Okay, let's say B just joined the system. Let's say B just joined this point, all right? It senses the medium. Okay, the medium is free, right? the medium is free. B just joined the network. It senses the medium. Oh, the medium is free. If B had waited only this amount of time, it would send at the same time as the destination sends the acknowledgement, right? And what could be the problem here? If B sent at the same time as the acknowledgement, what would be the problem? Anyone? Exactly, there could be a collision and the acknowledgement is lost, right? And the acknowledgement is lost. So just 1 second, please. So the acknowledgement would be lost. All right, now, if you have to give, you have to consider B and D. Who would you give higher priority to? If you have to give B and D priorities, who would you give higher priority to? B or D? So if you now you have two options, right? B and D. D want to send acknowledgement. B want to send a new data package. All right. Who would you give higher priority to? B or D? Anyone? Okay, so just toss a coin and give me an answer. All right. D. So two people say D. Okay, Aditya, why did you say D here? Shadan as well. Okay. So Aditya, you said first, why would you give D higher priority?
So the acknowledgement can be sent, and the data that was previously being sent can be finished transmitting, and then the next process can be processed.
Exactly. You want to complete this transaction as soon as possible, right? Because if the source waits for too long for acknowledgement, it may assume that the acknowledgement is lost, right? And it will double the contention window. You remember it will retransmit the data packet, and you would waste network bandwidth, right? So that's why you have to give D higher priority than B. Okay, and this is where you see that how D gets higher priority, because it have to wait only for SIFS, right? B has to wait for DIFS, which is longer. So by the time D senses the medium to send, it knows that the medium is busy, all right? So, and because the medium is busy, all right, B has to draw a random number, okay? Now, if you look at the next step, what is a random number that B draws? What is the value of random number that B draws from the next step? If you can see, all right, 6, right? So that means B store number 6 here. So that's why it's wait 1, 2, 3, 4, 5, 6 time units. And then after that, B can transmit. All right, so that's B here. Okay. All right. So any other question here? Now you understand why we use SIFS and DIFS, right? So SIFS is reserved for frames within one transaction, right? One transaction, so that we can finish the transaction as soon as possible, as quickly as possible. And DIFS means this new transmission belongs to a different transaction, so you have to wait a bit longer, okay? All right. So this one shows that B, let's say assume that B is waiting to send data. B would wait for 6 time units and then it will send data here, okay? All right, so now there's another detail about this slide that I want to tell you, which is NAV. So this is network allocation vector, okay? So what is a network allocation vector? All right, so basically it's just a value, but that's the name. Now, instead of so let's say A transmits the data, all right? In the data packet, sorry, S will tell the other station that this is the duration for the data packet. Okay, this is the duration for the data packet, for the data frame. Now, the other station knows that if this is the duration for the data frames, the destination will have to wait for SIFS, right? And then the destination will have to send the acknowledgement frame. Usually the acknowledgement frame has a fixed length, right? The length of the data frame can be varied depending on how much data a source wants to send. But the acknowledgement frame usually has a fixed length. So the other station can compute the interval between the data sending here up to this point, all right? So it can calculate this value. So assume this value is T. So a station, when it knows that it cannot use the medium for T, let's say time units, right? And what does it do? It just go to sleep or do something else or does something else for T time units, right? So basically it records T in a value called network allocation vector. And then it knows that it has to wait for T time units before it goes back to send the medium. So it starts sending the medium at this point, all right? So when a station senses the medium like this, it's called physical sensing. That means it really tries to detect a signal. It's called physical sensing, all right? Physical sensing. Here, why it's used this amount of time to stay away from the medium. This is called virtual carrier sensing, all right? Virtual carrier sensing. That means it doesn't have to sense the medium, it doesn't have to sense the medium physically. It knows that it has to wait for this amount of time. So it's called virtual carrier sensing, virtual carrier sensing. Virtual because it does not really sense the medium physically, right? It just wait for this amount of time before it goes to the next step, okay? All right, any question? Okay, so if not, then we go to the next slide. All right, so we've seen this before, right? We've seen this before. We have transmission range and detection range, right? So these are the ranges that we use to detect signals, right? So when we say that, oh, we sense the medium to see if the medium is free or not or busy, the signal has to be within these ranges, okay? Because at this outside here, the signal cannot be detected, only these two ranges, all right? Okay, now we have a problem called hidden terminal problem, okay? So what does that mean by hidden terminal problems? Oh, first, when we talk about collision only happen at a receiver, okay? So let me show you what at a receiver. What it means is if A and B both send to C, okay? If A and B both send to C, then there would be a collision here, okay? Now, if you have the same configuration, and let's say C sent to A, and B sent to C, all right? B sent to C, and C sent to A, then there would be no problem, okay? Sorry, no, there may be a problem if, no, there could be no problem if the signal from A does not interfere at B. Sorry, yeah. So that means this is far away from each other, okay? If A and B are far away from each other, all right? So if B sent to C, and C send to A. You see that you may think that there's a collision here, right? Right, but it's not a collision at C, because B is receiving only from C is receiving only from B. All right, and it's sending to A. Now, if A and B are far away from each other, that means they don't have any interference. Then this is not a problem. Okay, this is not a problem. What it means is contention only happens at a receiver when you have two or more signals collide at a receiver. Okay. In this case, it's not a collision because B is receiving only from one station and it's sending to A. And if A is far away from B, then there's no interference. Okay. All right. So that's why we said here contention matter only at the receiver. All right. So hidden thermal problem. What is the hidden thermal problem? Okay. So this is the example. All right. So basically, this is the detection range of A. Okay, detection. All right, the detection range of A. Okay, so you can see that, remember we said that they have to sense the medium to know whether the medium is free, right? If the medium is busy, so they have to wait. The problem here is X is too far away from A, right? X is too far away from A. So when A sent to B, the signal has not reached B yet, right? The signal has not reached B yet. So that's why X cannot detect the signal. But X is too far away from A. So that's why X cannot detect that A is sending something, right? Because X is too far away from A. B can receive from A, but X is too far away from A because the signal basically disappears at this boundary. So that's why X cannot detect the signal from A. So it doesn't know whether this medium here is free or not, right? So that's why X sent at the same time and the two signal collide at B, okay? So this is called the hidden terminal problem because A is hidden from X, right? And the same thing, X is hidden from A as well. If the range of X is outside, let's say the range of X is, sorry, around here, for example, right? So it can reach B, but it cannot, A cannot detect the signal from X. So this is called hidden terminal problem, okay? So what it means is no signal does not mean that it's okay to transmit. All right, no signal means that it's okay to transmit. And in this case, because X is outside the detection range of A, okay, or the sensing range, usually call it the sensing range, okay, of A. All right. So the solution to this is using a RTS, CTS dialog, request to send, clear to send, okay. And later, so the first person is Karn in 1990 proposed this dialogue. We'll learn about that later. Later, another researcher proposed to use acknowledgement even to increase the reliability, all right? And then this is developed into the DCF of AO 2.11, okay? All right, so let's see how we use RTS and CTS to solve the hidden terminal problem. Okay, so first, when this is the source and this is the destination, if S wants to send a data frame first, it has to send an RTS message, right? It's called request to send. And any node that hears this message have to defer medium access, okay? Have to defer medium access. Why? Because in this case, yeah, this node will defer because here the RTS, right? Remember, this is the range, right? The transmission range. So this is the transmission range. Okay, transmission range. Okay. So this node had here this, it will defer. Now assume you have another station here, right? Another laptop here. Let's say this is A. Now, if A hear this message and it want to send a message to D, it should not send, right? It should not send because it hear the request to send. So it have to defer as well. When we say defer, it means wait, okay? Defer means wait, right? So D will receive the message. It's sent on CTS, right? Send a CTS. Now, when another station hear the CTS, it have to defer as well. Okay, so this node had to defer, right? So whoever hear RTS and CTS have to wait and defer, right? And then after that, S will send the data package to D and D send back acknowledgement. Okay, all right. So that's the basic of RCS and CTS. Okay, and this is to avoid the hidden terminal problem. Okay, so you can see here. Let's say this is B, right? When B, okay, so this B here. When B hears the CTS, it knows that D will be receiving data from S, so it should not send, right? So remember in the previous example, this is what we have A, B, and X here, right? A, B, X in our previous example, A, B, X. And A and X may send packets that collide at D. But in this case, because D sends a CTS back to S and B hears, or X in the previous example hears the CTS, it knows that it has to wait, okay? Right. Okay, so and then that means now everything around S and D are clear. So everyone around here know that they have to wait. So S can send data and D send acknowledgement. Okay, all right. Okay, and then we also have the backup interval as before. Remember before we have data and acknowledgement only, right? Now with RTS and CTS, we extend the algorithm to sending RTS first instead of sending data, right? And then when a node fails to receive CTS or acknowledgement, right? Now before, if a node fails to receive acknowledgement, then the windows, the contention window is double. But in this case, if a node fails to receive CTS, we can also double the contention window, okay? So now we add RTS and CTS into the equation, all right? Okay, any question? All right. So let's consider some example. And now you can see the use of SIFS, right? Okay, so the source and the destination. So the source has data to send. So it senses the medium, and the medium is free for the IFS. So it sends RTS first, okay? So the destination, so when you see this kind of diagram here, what it means here is the x-axis represent the time, right? The x-axis represent the time. And then we have the source here, the destination here, and other station here, right? But as we go from left to right, it represents the time. So the destination, again, after receive RTS, waits for SIFS, right? And it sends CTS. The source receives CTS, clear to send, right? CTS and for clear to send. It waits for SIFS and it sends data, right? The destination receives the data, waits for SIFS and send acknowledgement, okay? Now you can see why we need SIFS here, right? Because we give different packets, different frames of the same transaction, higher priority, so that they can complete the transaction just like before, all right? Okay, and all right, so now assume that a station B, right? A station B joins the station, right? Let's say in the previous example, we have B, right? Okay, is it? Oh, let's say X, right? So this is A and B source execution. Let's say X just joins the networks. the medium is busy, right? So remember, X have to draw a random number, okay? So it draw random number, and in this case, it draw number 3, right? So it's draw number 3. Now, at this point, it keeps sensing the medium. Now it have to use physical sensing. At this point, it senses that the medium is free, right? Now remember, it have to weigh DIFS, okay? It have to weigh DIFS here, right? And at the end of DIFS, it senses the medium again, right? So the medium is busy, right? So that means it cannot do anything. It has to keep waiting. It waits until DIFS, right? Again, it's wait DIFS here. And now the medium is still free. So this is when it count down n equal to 3. Okay, it start counting down using this value it drew earlier. And after that, it can transmit this packet, right? Send RTS here. Remember, we have to send RTS first, right? It send RTS to another station, for example. And this RTS is from X, okay? All right, any problem here? Okay. All right, so that's one thing. Now, talking about other stations. Okay. Why waited for 3? This 3 is drawn from, remember, from an interval. This is a random number drawn from 0 to 7. Does that answer your question, Samyak? Okay, right. This is random number drawn from 0 to 7, right? Okay, now we're talking about physical sensing, right? So basically when the source senses the medium here is physical sensing. Now we're talking about virtual sensing. Okay, now you can see here we have network allocation vector. Sorry. Oh, no, it's not here. This one. Okay, so when a station hears the CTS, sorry, RTS, right? Now inside the RTS, it contains a value which is the duration of the data packet. Right? It doesn't have to include anything else, only the duration of the data packets, right? So let's say this data packet takes time, let's say the time is K, right? K time unit, for example, all right? So this information K time unit will be included into RTS. So when a station receives the RTS, it gets number K, right? Take K time units. So it knows that now it has to add the duration of the CTS. It has to add the duration of the acknowledgement, and it has to add three times SIFS, right? So it has to add, and that will be the time from here to here, okay? So assume this is a value, let's say T1, okay? Then this station will wait for T1 time units. So maybe it goes to sleep, does something else, and then it goes back after T time units to send the medium physically, all right, to send the medium physically. All right, similarly, if a station receives CTS, now inside CTS, we also have the value K is copied into the CTS as well, all right? So when a station receives CTS, it knows that it has to take K plus the duration, sorry, K plus the duration of the acknowledgement plus the duration of the two SIFS intervals, right? And it gets this value. So you can see duration that, which is this duration, assume T2. So now this station knows that it had to wait for T2 time units. So it goes to sleep, it does something else and comes back after T2 time units to sense the medium, right? Similarly, another station here, the data packets. Again, inside the data packet, it has value K. So this station knows have to add to K the duration of acknowledgement, one interval of SIFS, and it gets this value T3. So it goes to sleep for T3 time units or does something else and come back to send the medium physically if it wants to send data. All right. So this is called network allocation vector, right? And different type of packets can give you different time of value depending on which frame you receive. Okay. So you can see in this example here. Right. So when S and RTS, this station can hear the RTS, so it can calculate the nav with the RTS, right? It can calculate this, all right, with RTS. So this station can calculate this. So it would get T1, all right? And then when this station hear the CTS from D, it can calculate nav of our CTS, right? And then this would get T2, right? And assume that data. So assume another station joins at this point here. Another station join at this point to hear the data, right? So this station can hear the data. It can calculate the nav using the data packet, right? Data packet. And it gets T3. So it waits for T3, all right? And that's how collisions can be avoided, right? Okay. All right, so this is a summary of what we just said before earlier. I'm using RTS, CTS, yes, and SCA. And this is what I've been talking about. We can have physical carrier sense. So that means the station actually senses the medium. Or we can use something called virtual carrier sense using the network allocation vector. All right, we use the duration from RTS, CTS, and data to calculate the time that a station has to wait, right? And we use collision avoidance. Okay. Now, my question to you is, even with this scheme, RCS and CTS, right? Is collision completely avoided? Is collision completely avoided? Anyone? Is collision completely avoided? Right, exactly. So Abdul Kabir, yes, very good. You still have collision of RTS, right? Assume S and then X here. They join the network at the same time. They senses the medium at the same time. They wait for the IFS, and both of them still see the medium is free, right? They would send RTS at the same time as well. Okay, they would send RTS at the same time. So that would be collision. All right. So there can still be collision of RTS, right? But then in the next time, they have to try a random number, and hopefully each of them try a different number. So we may not have collision in the next time around, they try again, right? Yeah. So again, collision of RTS still happen, right? As in this example, both of them try at the same time, the medium is free at the same time. They both wait the IFS and transmit RTS at the same time. Or as in this example, right? You can have another station, this is X, you can have another station named A. And A may try the same number 3 as well, right? Both of them try the same number, right? Both of them true the same number. And if they true the same number, they wait for 3 time units, they send RTS at the same time, there would be collision, right? And if we have a collision, then what would happen? If we have a collision, then I cannot move forward. Remember this? if we have a collision of RTS, then CTS will not be sent back, right? So when a node fails to receive CTS, the contention window is doubled up, right? And now they have to draw a number. So hopefully the two stations will draw two different numbers this time, right? So the last time they drew the same numbers, but hopefully now they would, because the interval is larger, hopefully they will draw two different numbers, all right? So yes, CS min is always 7, yes. CS min is always 7, yes. Okay, so, right. Okay, so this is a summary of what we've learned so far, okay? And this is another example. So I will go through this example and then we continue the lecture next time, right? Because I want to you to have the last example to study to understand the material for DCF, CSMA CA with RTS, CTS. Okay, so this is the last example, and then we stop the lecture. Okay, so in this example, we have 4 stations, right? S1, S2, S1, R, and X. Okay. So let's see here now. S1 and S2 both want to send to R. All right. And then, so basically, yeah, so they both want to send to R. Okay. All right. Or maybe one of them, they want to send to someone else, but that's so both of them want to send to R. And then X is a neighbor of R here. Okay. Right. Again, the x-axis is the time, right? X-axis is the time. And now we have the activity for S1, S2, S1, R, and X on this side. So at this point, the channel is busy, right? So S1 and S2, they want to both send at the same time, but the channel is busy, so they wait. So why they wait here? They draw a random number. It draws a random number, right? It draws a random number. So S2 draw number 9 and S1 draw number 5, okay? When the channel becomes free, both of them wait for the IFS, right? So again, in case someone else has SIFS, and that person would get higher priority. In this case, we don't have anyone in the system with SIFS waiting time. So both of them can start countdown from the timer, right? So obviously S1 gets to send first because it drew number 5 and S2 drew number 9, right? So after 5 time units, S1 transmits a request to send, okay, RTS. Now S2 will freeze the timer, right? So it will freeze the timer. So now it has 4 time units left, so it freezes the timer there, okay. All right, so, and then R received the RTS. It waits for SIFS, send back the CTS. S1 waits for SIFS, send the data. And then R waits for SIFS and send acknowledgements. All right. Okay, so now that's the transaction between S1 and R. Now let's look at what S2 and X do while S1 and R are exchanging frames. So S2 will hear the RTS from S1, right? Because S1 is here, so it sends an RTS. So obviously, it can hear the RTS from S1 because it's a neighbor of S1. So when it hears the RTS, it knows the duration of the data packets, right? So it can calculate the total waiting time. It will add the data packet with the CTS, with acknowledgement, with IFS. That's why it came up with this value for the network allocation factor. So now it will go to sleep or it will do something else for this amount of time. All right, so we call this T1, right? And X, obviously X will hear the CTS, right? Because R is transmitting the CTS. It will hear the CTS. So, and inside the CTS, that will be the duration of the data packet, data frame. So X will add the time of the acknowledgement and this SIFS to the duration of the data frame to get this value, right? So call this value T2. So it will have to wait for T2 amount of time, all right? All right, so, and then now S2 waits for T1 time unit. So now it goes back and it senses the medium, right? So now this is virtual carrier sensing, right? This is virtual carrier sensing, all right? Now S1 still want to send data, right, to R. So that's why it have to come back from here. It senses the medium. So this is physical carrier sensing, right? Because it have to make sure that the medium is free for the IFS time units, okay? And because it is free for the time unit, it starts countdown from number 4, all right? Now S1. Now if S1 want to send again, right? If S1 want to send again, it has to draw a new number, all right? Have to draw a number. Why? Because remember, even though it was sending before, right? Remember when it was sending before, that means the medium was busy, right? S1 was sending before, that means the medium was busy. And when the medium is busy, you have to draw a number before you can send, right? Even though S1 was sending, the channel was busy because of S1, but the channel was busy. So S1 has to draw a number. So this time it draw number 7, okay? And then most of them count down, right? So S2 will count down 4 time unit. S1 count down 4 time units. So this reaches 0. So S2 can send an RTS. S1 has to wait 3 more time units in the next round of transmission, all right? Okay, so that is the example to illustrate how RTS, CTS data acknowledgement works with DCF, medium access control. Okay, any question here? Anyone? All right, so if there are no questions, then we can stop the lecture here. So I will stay for about